Hi students, how are you? I think it's fine, and I think all of you checked my videos of the previous classes of periodic table, isn't it? If it is not, at first please check my previous videos of the periodic table and then attend this class. Myself, Tanmoy Dotto, Assistant Professor, Department of Chemistry, the JS College of Engineering, welcome you in the third lecture of periodic table. And today we'll discuss about the diagonal relation, we'll discuss about the screening effects or effective nuclear charge, and we'll also calculate, or I will show you that how to calculate the effective nuclear charge. And also we will discuss about the ionization potential, and there are some factors also on which ionization potential depends on. I will show you that on which factors ionization potential depends on. So without further delay, let's come to my class. Okay, so now what is the diagonal relationship? You know, in case of periodic table, according to the group, I already told you in the previous class that according to the group, there you can expect some similarities of the properties, some physical properties, some chemical properties. You can expect the similarity, but not only the according to the group, there may be another kind of a relationship or the similarities of the properties can be obtained from the periodic table, and that is according to the diagonal relationship. Diagonal relationship means it is the second period, okay, and a second period, and it is the third, okay. So there are some kinds of similarities occur in between second period and third period elements which are exist diagonally. Diagonally means here lithium, that element has some kinds of similarities of the properties with the magnesium. Beryllium, that element has some kinds of similarities with the aluminium. Boron, that element has such kind of similarity with the silicon. So that diagonally exist a relationship with the diagonally exist elements, that is called actually diagonal relationship. So you can expect the question in that way, what is the diagonal relationship? Then you have to write down the definition of the diagonal relationship and also the examples, and you have to show in that way that how the elements are related with each other. Okay, now there is another important term or topic in the periodic table, most important, one of the most important term, that is called actually effective nuclear charge. So I think that name, that effective, okay, from that name, there is another thing that is indicated, that what we are discussing till now regarding nuclear charge, that is not the last word. Why? Because that nuclear charge, actually it is not felt by the all the electrons equally. That's why they are the term effective that came before the nuclear charge. I will show you that, for example, if you think that this is the nuclear charge, okay, and this is a nucleus. So nuclear charge of what that electron, what is the amount of nuclear charge felt by that electron, that will not be equal with that electron. I mean that what is the nuclear charge that is felt by first electron, that same charge will not be felt by the next electron. Again, if there is another electron, so that electron also it is not felt the actual nuclear charge. Or more specifically, if I tell you that nuclear charge will be decreased one by one cell when it comes from to that electron to that electron to that electron, gradually nuclear charge will be decreased. Okay, so that's why the term effective nuclear charge is here. Okay, so now try to understand that why it is effective. That means why the nuclear charge is decreasing. Okay, so why it is decreasing? If I tell you that in case of that electron, okay, so when the nuclear charge will go to here, that means before that cell there is already another cell. So that cell actually acts like a screen. Okay, so what is the role of the screen? The role of the screen is that it to guard something. or shield, okay, in the time of fighting, okay, that's some shield. The shield means to guard something, isn't it? So the same role it is played by the orbitals also, the orbitals which exist before that particular electrons. So that's why it is called also shielding effect or screening effect, okay, keep in mind. Also there is another name that is called the screening effect, either shielding effect or it is called the screening effect. Why? Because it screened the nuclear charge, okay. So nuclear charge is screened by the inner orbitals, okay. So this is the inner orbitals with respect to that electron, it is the inner orbital with respect to that electrons, okay. So that's why it is called the screening effect and shielding effect, and and then we are using the term effective nuclear charge, okay. So original nuclear charge is not felt by that electron or that electron, so there we have to use the effective nuclear charge. That means after decreasing the nuclear charge, what amount of nuclear charge is felt by the electrons, that is called actually effective nuclear charge. Now look here, it is the equation of the effective nuclear charge, okay. So here look, Z effective means what nuclear charge is actually felt by the electrons, so that is called actually effective nuclear charge. Now Z, what is the Z? Z is the original nuclear charge, it is normally the proton number, okay. So you know that nuclear charge is generally equal to the number of proton present in that particular atom. So Z is its original nuclear charge, and this sigma, this is very much important, sigma is called actually screening constant or the shielding constant. That means how much nuclear charge is screened by all the inner cells, okay, because screening is possible only by inner orbitals, not by the outer orbitals. Because how is it possible? That means that orbitals can screen the nuclear charge, but if we consider that if there is any other cell, so that cell it is not possible to screen the nuclear charge for that electron, it is not possible. So that's why only inner orbitals are able to guard or to screen the nuclear charge. So that means sigma, if that can be calculated, I will show you how we can calculate the value of sigma. So sigma, that is the screening constant or the shielding constant, that means overall effect of the inner orbitals, that how much nuclear charge is decreased or the screened, that is called the screening effect or the shielding effect, okay. So now it is the equation, and that equation or that process is also called Slater's rule. According to the name of the scientist, that is called the Slater's rule. At first we have to make a group of the orbitals, okay. So according to the Slater's rule, there one is NS NP, that will be one set, and ND NF, that will be another set, either ND or NF, okay. So ND and NF, that will be another other group, okay. ND and NF, okay. So then you have to keep in mind the values of the screening, okay. Screening values means, for one is, you know that in each and every case, you know that for higher groups it will be 0, because in case of higher groups I already told you that for the higher orbitals it is not possible to screen the nuclear charge for the inner electrons. So for that case, in case of all the higher groups, it will be always 0. Now come to the point, for the same group, if we consider the same group, okay, so then for 1s the value will be 0.30. Same group means, for example, if it is 1s2, okay, I will also show you one example. If it is 1s2, then it's one electron will be screened another electron, okay. So here the value of the for same group electrons, like for one electron, first electron, it will be the value of the 0.30, okay. And n-1, no question, because it is 1s already, n-2, it is no question about this. NS NP, for the same group it will be 0.35, n-1, that means if it is 3s, then for n-1 is for 2, quantum number 2, under 2 how many orbitals or subshells are there, that in each and every case you have to take 0.85, and for n-2 then it will be 1, okay. That values you have to keep in mind, but more easier to keep in mind for ND NF. It will be same group, it will be 0.35, but n-2, n-1 both are the value of 1, okay. Okay, so now I will show you that for one example that it will be more clear to understand that how you can calculate the sigma value. Now come to the point that how we can determine the screening effect or the screening constant or the effective nuclear charge for any of the electrons which exist in any particular orbital. If you take the example of any element which has the atomic number Z equal to 26, any of that example, then what you have to do, first of all you have to write down the electronic configuration in this way. Okay, so then in this way means you have to at first you have to write down in the simple way 1s2, 2s2, 2p6, 3s2, 3p6 like that way. Then you have to make the group. Okay, so make the group means 1s will be one group, it is the 1s one group. 2s 2p, ns np, that means 2, 3, 4, 5, 6 whatever, the 2s 2p will be another group. So here 2s 2p, and you have to write down the total electrons here. Okay, 2s 2p you have to write down here. Same way you have to write down 3s 3p, that equals to 8. Okay, then you have to write down nd and nf differently. Okay, so nd either nd one group and nf another group. Okay, so nd, then 3d, here nd means 3d, so 3d equals to 6 here, and 4 is 2. So in this way you have to at first write down the total number of electrons according to the group or group wise. Okay, then what you have to do, consider for first electron that is the 1s2. Okay, if it is 1s2, and if in the question paper if it is mentioned that for the first electron for 1s orbital, for the first electron what will be the sigma value or Z star value. So you have to first calculate the sigma value according to the Slater's rule. This is the Slater's rule. So look here, if we consider the 1s, then higher groups will be always 0. So we are I am not considering each and every time to use to tell that thing that will be 0. But same group 0.30. Same group means here 2 electrons. So one electron will screen another. Okay, so for one electron we are considering the screening effect for one electron. Okay, so in these 2 electron we are considering the 1 electron for 1s orbital. So another electron screen that electron also. So that means that will be 1 into 0.35. Okay, so there are 2 electrons, so we are considering for 1 electron. So remaining electron will be 1. So that's why we are considering 1, and for each and every electron the value is 0.30. Okay, for the same group here it is the 0.30, so it will be 1 into 0.30 equal to 0.30. It is for 1s, and for higher orbitals or higher cells it will be always 0. So I am not considering in that case when we are considering the 1s. When we are considering 2s or 2p, then what happened? If we considering 2s or 2p, then here total electrons 8, isn't it? So if it is here total electron 8, that means for one electron another 7 electron screen that electron, isn't it? So that means we are considering 7 electron for the same group. So here it will be 7 into 0.35, because for the same group, look here for the same group it is the ns np, it will be 0.35. For remaining 7 electrons it will be 0.35. Okay, so 7 into 0.35 for 1 electron it will be 0.35. So 7 electron it will be 7 into 0.35. So now remaining 2 electrons. Okay, 2 electrons will be n minus 1. Okay, n minus 1, why? Because here it is the principal quantum number 2. So n minus 1 means it will be 1. So under 1 there will be 1s. So 1s will be 2 electrons. 1s has the 2 electrons. So that means here it will be 2 into 0.85. Look here, n minus 1 0.85. So here 2 into 0.85. Then total value will be 4.15. It is for 2s 2p. If we consider 3s 3p, look here for 3s 3p, what will be the value? Same case here it will be 7 electrons will be 7 into 0.35. Okay, same case previously was 7 into 0.35. Here same case for 7 into 0.35, because for 8 if it is the total number of electrons are 8, then obviously for 1 electron another remaining 7 electrons screen that 1 electron. Okay, so here 7 into 0.35 plus remaining electron n minus 1. N minus 1 means if it is 3, n minus 1 will be 2, isn't it? 3 minus 1 equal to 2. So that means here 2s2p. So under 2s2p, total electron is 8 here. So 8 into 0.85, n minus 1, 0.85. Okay, so 8 into 0.85. Then n minus 2, here n minus 2 exists. In the previous case there was no n minus 2, but here n minus 2 present. So we have to consider n minus 2. For n minus 2, each and every electron 1, sigma value 1. Okay, these are actually sigma values, okay, screening constant values for each and every electron. So here it is the 1. So if it is the 1, then 2. Why? Because with respect to 3, the n minus 2 is the 1. So 2 into 1. So 2 into 1 means it's 2. Okay. So then total value will be 11.25. Next case. In case of 3D, okay. So in case of 3D, come here, either ND or NF, you have to consider that example. So in case of 3D, here you have to make the group first of all in that way. So we have to consider that 3D6. So if it is 3D6, for same orbitals, the 5 electrons will screen 1 electron. We are considering for 1 electron. So if their total number of electrons are 6, then 1 electron will be screened by the 5 electrons. So here it will be 5 into 0.35 for same group. Look here, same 0.35. But for n minus 1, it will be 1. For n minus 2, it will be 1. So that means here look, so it will be 5 into 0.35, and remaining all the electrons, okay, remaining all the electrons means it will be either n minus 1 or n minus 2, whatever, that will be considered as the 18. Why? 8 plus 8 plus 2, 8, 16 plus 2, that means it is the 18. So remaining 18 electrons will be under 1, so it will be 18 into 1, so that means it will be 19.75. Okay, so now here last point in 4s, if we consider the 4s, so 4s will be under that category. So if we consider the 4s, then what happened in case of 4s? Look here, for the same group it will be 1 into 0.35, and then n minus 2, that means 3, so 3. Okay, so 8 plus 6, that means 14, so 14 will be 0.85, because this is the ns. So 0.85, so 14 into 0.85, and then n minus 2, or either n minus 2 or all the other orbitals, okay, below n minus 1. So we have to consider as the 1. So here either 2 or 1, all will be considered as the 1 contribution as a sigma for each and every electron. So 8 plus 2, 10. So 10 into 1, total value will be 22.25. Okay, so this is the total calculation of the effective nuclear charge for each and every case. And look, there is an interesting thing that when we move to that electron to here and that electron to here, that sigma value that is increasing. And you know that if sigma value is increasing, that indicates that Z star value or the effective nuclear charge value, because effective nuclear charge equals to 26 minus sigma, because here it is the 26, Z is the 26. So look here, if sigma value is increasing, that means Z star value will be decreasing, isn't it? So effective nuclear charge will be decreased when we move to 1s to 4s. That means 4s electrons are loosely bound with respect to the 1s electrons. Okay, so that's why actually for that reason or this reason actually when we will move to the 1 electron, 1s, 2s, 3s, 3p in this way, the last electrons are most loosely bounded, because due to screening effect, nucleus is unable to attract in the similar way by which the first electrons will be attracted. Another thing what you have to keep in mind, that here it is one star mark. Do you know why star mark? I think that question already arose in your mind. That when we are considering the 3D, so generally what happened, 5 into 0.35, that's good. But why here 18 into 1? Here n minus 1, n minus 2. But n minus 1 started with here and n minus 2 started with this, isn't it? So that's why here star marks. That star marks means here it is not actually n minus 1. For 3D or for ND or NF, you have to keep in mind that all the electrons below that set, either ND or NF, all the electrons below that set, not exactly n-1 or n-2 or like that. All the electrons below that set, you have to consider that the contribution will be of 1. Either under same principal quantum number, or it is the below that principal quantum number. That you have to keep in mind. That's why I am giving here the star, because you have to keep in mind that is not restricted to like n-1 or n-2. That is applicable for all the electrons which is actually below that set of the orbitals. Okay. Now we will discuss about the next important term of the periodic table, that is called the ionization energy or ionization enthalpy. Now what is the ionization energy? Ionization energy or ionization enthalpy means it is the energy required to remove one electron from an isolated gaseous atom in its ground state. So there are so many conditions for the ionization energy to determine the ionization energy. First of all, the electron which will be removed or which we are trying to remove, that electron should be the outermost cell. Okay, that means the last electron of the atom. This is the first condition. Second condition, the atom should be in the ground state or stable state, and it should be in the gaseous form. Okay, or it should be isolated state. That means the one atom, that there is not any other influence of the any other atom. That means it should be isolated gaseous atom in its ground state. Okay, so now if we consider here that M is the any isolated gaseous atom. M is the any isolated gaseous atom. Then if we want to remove the electron, then we have to apply the I or IP, whatever. So I am writing here IE for ionization energy. We have to give the energy. Then what happened? Then M will be one positive charge plus E. That means if one electron is coming out from the atom, then what happened? There will be one cation which will be produced from the atom. So M is converted to the M plus E. So that indicates that IE, that amount of energy we have to apply, that IE is called actually ionization enthalpy. Okay, so there may be we can express it either kilojoule per mole, or we can express kilocalorie per mole. It is kilojoule per mole of atom, mole of atom actually. Here it will be mole of atom. Okay, so that things you have to keep in mind. Okay, so now what I am telling you, that why ionization energy is very much important, why it is the value is very much important. That value actually predict that how much tendency that particular atom has to be the cation or to be converted to the cation. If the ionization energy of that particular atom is very lower, that indicate atom has a tendency to be to be converted to the cation, corresponding cation. Or if the ionization energy is very higher, that means it is highly stable in the atomic form. It has no tendency to be converted to the cation. Okay, values are in that, from that point of view, it is very much important. Okay, so now if it is first electron when we are removing, actually when we are defining the ionization energy, you have to keep in mind there it is generally the definition is for first ionization energy, because ionization energy may be first, second, third in that way. But what definition we discussed, that is the from the first from the point of view of first ionization energy, because in the definition there it is mentioned that for the isolated gaseous atom. But for the second stage, look here, if we continue the process, if we continue the process, then what happened, that M plus IE2, here it is not the atom. Okay, that's why I am telling the first case, here the definition mainly applicable. So then here it will be M2 plus 2E, isn't it? So here in the second case, there we are taking it is as the IE2. Okay, so now the question arises that what is the value of IE1 or IE2 or IE1? That means if we compare the values, then it will be always IE2 greater than IE1. Why? Because look here, that in case of IE2, if we consider the IE2, then what happened here? It is already in the cation. And you know, I told you when I discussed in the time of the atomic size or atomic radius, I told you at that time that M plus means here one proton is already greater than one electron. Here one proton is already greater than one electron. So that means that indicates that already there is a high attraction force to the last electron. If proton is higher with respect to electron, then there must be greater attraction force. So if there is greater attraction force, here it is very much high energy required with respect to the previous case. Here electron and proton, they are same, but here it is not. So here greater energy required to remove one electron. So that's why IE2 will be always greater than IE1. If there is IE3, it will be again greater than IE2 and IE1. Okay, so that sequence you have to keep in mind. Now come to the point that on how many facts or factors are there on which ionization energy or ionization potential depends on. Now come to the point that on which factors that ionization potential or ionization energy depends on. That factors we have to keep in mind, because from that factors there you can expect the questions. Okay, so if we consider first factor, that will be atomic size. That is very important, that very much important. Okay, so atomic size, that indicates the attraction of the nuclear charge or nuclear force. Okay, that depends on the nuclear charge. For example, if the size is lower, that means attraction force higher. Size lower means, if it is lower, that means attraction force higher. Its attraction force will be higher. It will be higher. Okay, so if size that is lower, attraction force will be higher, and its opposite, vice versa. If size is higher, the attraction force will be lower. Okay, so that means look here that from the size we can conclude what will be the attraction force. Now if attraction force higher, that means if attraction force higher means you have to apply more energy to remove the electron from the atom, isn't it? So we can get the information of the attraction from the size value of the atom. So we can conclude that already we discussed in the previous class that with increasing the atomic size, or according to the period, you know that atomic size it decreases, and according to the group it increases. Okay, so there are two factors. According to the period, the atomic size that is decreases, because we can expect from that fact that according to the period, the nuclear attraction force will be more strong. Okay, but according to the group, nuclear attraction force will be lower, as the size of the atoms, or the size of the atoms, that will be actually increased, because the attraction force actually decreased according to the group. So that means ionization energy or ionization potential, that can be reflected in the same way, that according to the period it will be increases. Why it will be increases according to the period? Because look, according to the period, size decreases. Size decreases means that attraction force according to the period it will be increased. So obviously ionization potential will be increased. That means with the nuclear charge, or with increasing the nuclear charge, it proportional to ionization energy. If nuclear charge increases, then obviously ionization energy or ionization potential will be increases. Okay, but according to the group, look here, according to the group, it will be decreased. That means ionization energy will be decreased. Why? Why it will be decreased according to the group? Because according to the group, the size that is increasing, atomic size, that means nuclear attraction force that is decreasing. And I already told you, if nuclear attraction force decreases, then obviously you have to apply less amount of energy to remove the electrons. So that means here the ionization energy will be also decreases. Okay, so here all the other facts are included in the atomic size, starting from nuclear charge, which I already told you, and regarding the screening effect. Here when I am telling that nuclear charge, you have to think about it is the effective nuclear charge. We already discussed about the screening effect. So actually what amount of nuclear charge is felt by the electron, that is effective nuclear charge. So always nuclear charge means it is reflecting the effective nuclear charge. Okay, so you have to think that it is the effective nuclear charge. Okay, so effective nuclear charge, it will be increased according to the period. So ionization energy will be increased, and according to the group it will be decreased. Okay, so that fact is very important, and from there you have to understand that what is the trend of the ionization energy according to the period and according to the group. That is also important parameter according to the period and according to the group, which you have to keep in mind. Now come to the second factor, that is very important. Okay, you know, half filled and full filled subcells are very stable. I can give you one example, that hydrogen, helium, lithium, beryllium. So if we consider beryllium and if we consider the boron, okay, so beryllium, it is the last electronic configuration 2s2 2p2, outermost it is the 2s2, outermost electronic configuration 2s2. Okay, and boron, that will be 2s2 and 2p1. Okay, so here it is a 2s2, but here 2s2 2p1. Okay, so look here. Now if you want to apply the energy to remove that electron, which is highly stable, you know that 2s2, it is the full-filled subcell. So you are trying to remove one electron from full-filled subcell. So you need the high energy. But here 2p, look here it is the only one electron, isn't it? Here it is the only one electron. So you can easily remove the electron even less amount of force, because boron also has a tendency, if it is possible to remove the one electron, it will get the stable configuration. So that's why also boron wants to lose the electron. Okay, so then it will get the stable configuration. So that means though beryllium and boron, it is according to the period, and expected that beryllium to boron according to the period, ionization potential will be increased. It is expecting that ionization potential will be increased, but actually it is not increased, because that beryllium has the higher ionization energy or ionization potential with respect to boron. That may be the question also, because it is the not according to the trend, it is the exception. So that's why you have to keep in mind, and you have to explain from the point of view of the half-filled or full-filled subcell. Okay, I can give you another example also. If you consider the nitrogen and oxygen, it is also another important question. If you consider nitrogen and oxygen, then look here, nitrogen to oxygen, we are expecting that it is according to the period, so ionization energy should be increased from left to right, isn't it? But what happened if you consider, here is the electronic configuration 2s2 2p 2p3, but here 2s2 2p4. Okay, so I think all of you understand. Okay, so 2s2 2p3 means it is highly stable, and 2s2 2p4 means here oxygen has a tendency to lose one electron such that it can get the stable configuration. So here greater energy required to break the stable configuration, that means 2p3 half-filled. 2p3 half-filled means it is highly stable. So here greater amount of energy required to remove the electron with respect to that case. So that means this indicates that nitrogen to oxygen, it is according to the periodic trend, it should increase, but it is actually exception. Why it is exception? Because of the reason that here it is the half-filled, and here it is the not the half filled. So here we can easily remove the electron with respect to nitrogen. So this may be the also another question, that type of question which you have to keep in mind. Come to the next factor. If we consider the next factor, then I can tell you that types of orbitals or subshells are very much important, like S, P, D, F. So generally, depending on the penetration power, I will discuss in the next class that what is the penetration power. So depending on the penetration power, S has the higher penetration power with respect to P, D, F, and in this way, actually, S if the electron is coming out from the S, then you have to apply the higher ionization energy with respect to P, with respect to D, with respect to A. Okay, so if there is any such kind of question, like you have to compare that electrons are coming out where the differentiating factor is that they are different orbital or subshell, then you have to keep in mind the order. Okay, so if electron is coming out from S, because actually S has the higher tendency to keep the electrons more tightly, because it has the size of the spherically symmetrical, so it has a higher tendency to carry the electron density. So in this way you can also keep in mind that if the electron is coming out from the S, you have to apply the higher energy, then P, then D, then F. Another factor which you have to keep in mind, that electronic configuration. Electronic configuration means, for example, if you take the examples of the inert gases like helium, neon, argon, krypton, okay, so etc, etc. So that inert gases that are very high ionization energy, because that are stable configuration. All that inert gases have the very stable electronic configuration. Okay, so all the orbitals, all the subshells are fulfilled. So if it is very much stable, and if you want to remove the electron from that kind of inert gases, then obviously you have to apply more energy. Okay, so that factor is also very much important. Okay, so you have to keep in mind. So depending on that factor, we can predict that in which case there will be higher ionization energy or ionization potential, or in which case ionization enthalpy, and which case it will be lower. Okay, so so that means what we discussed today. So first of all, today we discussed about the screening effect. That is also very much important. You have to keep in mind diagonal relationship. That also you have to keep in mind. And we discussed about the ionization enthalpy and the factors related to the ionization enthalpy. Okay, so that all the topics you have to read carefully, because that is very, very important topics. Okay, and that's all for today, and we'll meet again in the next class. Take care. Goodbye.